Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Improper Integrals. And please, I'm reminding you to be an active learner as you're watching this video. By way of introduction, you recall from your arithmetic that we had things called proper fractions, and proper fractions were fractions like 3 over 4, where the numerator was smaller than the denominator. We also had things that we called improper fractions, where the numerator was larger than the denominator. Now, that didn't mean that these were good and these were bad. They were just different representations, and perhaps that's an unfortunate choice of words. Same thing happens with integrals and definite integrals. You remember that the fundamental theorem of calculus is often employed to compute the definite integral of a function lowercase f, for which an antiderivative capital F is known. Now, when we were talking about approximate integration, we were doing problems using the trapezoidal rule and Simpson's rule, where we did not know necessarily what capital F was. We still could do the problem. Moreover, this didn't just say that, but it said that if f is a real valued continuous function. You see, this theorem assumed that it was continuous. Well, sometimes it's not continuous, and we have to deal with that, and sometimes that makes this what we'll call an improper integral. And also, it said that when we had a function that was on a closed finite interval ab, then we had this equation. Well, we don't always have a finite interval. Often we have an infinite interval. So you see, we're going to be talking about things that don't fit this proper definition, and those are called improper integrals. Doesn't mean they're bad, doesn't mean we can't do them, it just means they're called improper integrals. And in our learnings, we're going to learn about what is an improper integral, and we're going to learn to call them either convergent or divergent. Those will be definitions we will learn, and we will learn how to solve applied problems that involve these improper integrals. So let's do an example here. Suppose you said you had the function y equal 1 over x squared, which is graphed here, and you wanted to try to determine what is this area going from 1 all the way to infinity. Well, it makes sense to think about this area as being the limit of this area, but as b goes off to infinity. So that's exactly what we're going to do. So we're going to start, and we're going to say the integral from 1 to b, we're doing this area down here, and that is 1 over x squared dx. Well, you add 1 to the exponent and divide by the new exponent, and again, you should follow all these calculations with your pencil and paper. So the antiderivative is going to be minus 1 over x. We'll evaluate that b and 1, and so this is from the fundamental theorem of calculus. Now here this is minus a minus, so that makes that a plus, and we get this. So, and another way to write this is 1 minus 1 over b. So if we were to do what we were talking about here, taking the limit as b goes to infinity to represent this area, the limit as b goes to infinity is going to be the limit as b goes to infinity here. Well, the limit of 1 as b goes to infinity is just 1, but this is 1 over b. That will go to 0, so this is 1. So you see the area from 1 to infinity for this is going to be 1. So this area shown right here is 1. Now, sometimes the areas are not finite, however. Let's try to find the area under the graph of y equals 1 over x. So here is the area from 1 to infinity of y equal 1 over x, and we're going to say, well, let's see what happens when we take the integral from 1 to b, and then we let b go to infinity as it's a limit. So let's do that. So a, then, the a that's up here, is going to be the limit as b goes to infinity of 1, the integral from 1 to b, 1 over x dx. We know that the integral of 1 over x is known to be the natural logarithm of x, and we evaluate that at b and 1. So this is ln b minus ln of 1, but the ln of 1 is 0. So this is the limit as b goes to infinity of ln of b. But in a previous section, we know that this is always increasing because its derivative is 1 over x. And so that is always a positive function, so this is always increasing. Therefore, this limit, since it's always approaching, it will go to infinity. And so the area under this from 1 to infinity is infinity. So we see that we can have a finite area, we can also have an infinite area. So even though the two graphs have somewhat similar shapes, one has a finite area, the other does not. So what we're going to do is we're going to talk about what is an improper integral, and here is one kind of improper integral we will not have going from a to b, we're going from a to infinity. So here's the definition, and we will use this to do these calculations. The improper integral from a to infinity of f of x dx is equal to the limit as b goes to infinity of the definite integral from a to b of f of x dx. Now, when the limit exists as a finite number, we say the improper integral converges or is convergent. If the limit does not exist or is infinite, then the improper integral diverges or is called divergent. Thus, this converges and this one diverges. And here's a note, and I'll leave it to the students to prove this. But in general, an improper integral of the form, the integral from a to infinity of 1 over x to the n dx, where a is greater than 0, is convergent for n bigger than 1, and it's divergent for n less than or equal to 1. Now that can be very useful, as we'll see in the next exercise. Okay, so we're supposed to determine whether each improper integral here is convergent or divergent, and if it's convergent, find its value. Okay, so here is, you're integrating from 3 to infinity of dx over the square root of x. Well, here, that's the same thing as x to the minus 1/2. And so that means that this is going to be divergent by that remark that I just made, because 1/2 is less than or equal to 1. So that is going to be divergent, and we see that it's divergent down here since 1/2 is less than 1. That area represented is infinite. Here you can see that 4 is bigger than 1, so it does converge, and here we do the calculation. Again, we use the definition. So the definite integral from 1 to infinity of 1 over x to the 4th dx is the limit as b goes to infinity of 1 to b, the integral from 1 to b, and this is 1 over x to the 4th dx, and we're going to calculate that. We will add 1 to the exponent and divide by the exponent. Now realize that this is x to the minus 4 when you're adding that, so this is the antiderivative, and you should follow all of these calculations. But then we use the fundamental theorem of calculus, plugging in b and plugging in 1, and we do the calculation. This limit here, as b goes to infinity, is going to be 0. Here's a minus, so the answer is this area is going to be 1/3. It is convergent. And here, we actually have to do some work because we don't have it actually that form. So we're going to divide this x to the 3rd into each of those terms. So the integral from 5 to infinity of this is equal to, I'm dividing x cubed into each of those terms, so that's going to be 1 over x squared and 1 over x cubed. We're going to do this now term by term. So this is going to be the limit as b goes to infinity, the integral from 5 to b of 1 over x squared, 1 over x cubed. I'm going to integrate each of those in turn, and again, check all these calculations, but here you add 1 to the exponent, divide by the new exponent. Here you add 1 to the exponent, divide by the new exponent. We evaluate this as b and 3. We substitute those numbers in. Now as b goes to infinity, both of these terms go to 0. And so we have to calculate this term. We have to be careful about our minus signs, but we end up with this is 11 over 50. So you see A and C were convergent. We computed them, and B was divergent. Here's another example. Determine whether this, the integral from 0 to infinity of 4e to the minus 2x dx is convergent or divergent, and If it is convergent, find its value. Okay, so what we're going to do is we're going to use the definition of an improper integral. This is the integral from 0 to infinity for e to the minus 2x dx. That's the limit as b goes to infinity. We put b up there. Now what we're going to do is we can pull the 4 out, and we say the antiderivative of e to the minus 2x. This is a substitution integral, so this is going to be e to the u, and then we divide by the change of variable, and we have minus 2. Again, make sure that you follow these calculations. We covered these in earlier sections. So now what we're going to do is substitute b and 0 in, and we're going to make note of the fact that e to the 0 is 1. And then this is going to be the limit as b goes to infinity of this. Now, as b goes to infinity, e to the minus 2b is 2 over e to the b, and that's going to go to 0 as b goes to infinity. So the answer to this is just going to be 2. The integral is convergent. Now there are other kinds of improper integrals. Here's 2 other types. And so if we were to go from minus infinity to b, that would be the limit as a goes to minus infinity of this definite integral. Similarly, if we go from minus infinity to infinity of f of x dx, the integral from minus infinity to infinity f of x dx, that's going to be the integral from minus infinity to c, plus the integral from c to infinity, where c could be any real number. And in order for this one to converge, both of these integrals must converge. Both must converge. Well, let's look at an application of these improper integrals that really comes up. So in a previous section, actually it was the very last lecture we did, we learned that the accumulated present value of a continuous money flow income stream of p dollars per year at a constant rate is this. We take the integral from 0 to capital T, and then we had this expression, and we actually computed that to be this, where k is the interest rate and interest is compounded continuously. Now suppose the money flow is to continue perpetually, and that means forever. Under this assumption, the accumulated present value of the money flow then is the integral from 0 to infinity. And that's going to be this by definition. And this is a calculation that we do. So we're computing this. We computed it right up here. We're just using this result. We're taking the limit as capital T goes to infinity, but as capital T goes to infinity, this goes to 0. So this is going to be P over K. And this actually then is a theorem. That's the proof of the theorem. The accumulated present value of a continuous money flow into an investment at a rate of P dollars per year perpetually is given by P over K, where K is the annual interest rate compounded continuously. All right, let's do an example of this then. So we want to find the accumulated present value of an investment for which there is a perpetual. That means you're going to infinity. Continuous money flow of $2,000 per year, and the interest rate is 5% compounded continuously, and we just use that theorem, plug it in. We get 2,000 over. That was the interest rate, or $40,000. Now, we're integrating a similar kind of thing, but a different application. This was a life science application that we talked about, when an amount P of radioactive material is being released into the atmosphere annually. And even though the radioactivity decays, the same calculation we talked about was this. So as T approaches infinity, the radioactive material released forever, the buildup approaches P over K. You see, it never goes away. It's here to stay. That's why scientists and environmentalists are so concerned about what do we do with radioactive waste. Now, another form of improper integral occurs when a vertical asymptote appears. Now, this is actually dealing with the fact where it is not continuous. So, for example, to find this area, 1 over the square root of x over 0 to 4, which is what we're going to calculate here, we note that f is not defined here, and so it is not continuous. And there's a vertical asymptote. So we're going to use the same kind of concept, but we're going to integrate from a to 4, and we're going to take the limit as a goes to 0. Okay, so that's what we're going to do here. This is exactly what we were talking about, and we're going to do this. This is going to be a. So the limit as a goes to 0 is the same as having a going to 0 here, and we can plug in 4 and plug in 0. And what we will get is that when you plug in 0, you get 0. When you plug in 4, you get 4. So the answer to this problem should have been 4. Now here's a more complicated one. This one has a singularity at 5. We're going from 4 to 5, but here's the graph, and you see it's going down negative like that. This is x equal 4, then it just keeps going negative, and here's the vertical asymptote that happens at x equal 5. So what we're going to do is we're going to calculate this as an improper integral, and we calculate this as an improper integral using this. We're going to say, well, this is going to be the integral from 4 to b, and we're going to take the limit as b goes to 5. And we compute that, but when we compute that at the end, we're going to get, and here are the steps, we're going to get minus 9 over 2. And of course, this is the area that we're finding, and that is a finite area. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.